Hot. Okay. Daniel, can you hear me over Zoom? Hot. Can you hear me? Okay. Very good. And hey, everybody. Let's do that. Cool. And we can zoom in a bit. Any questions so far? Anything? Plan for today, continue with transformation, or to give you a bit more preparation for homework 1. We are on 2D, we are still very simple transformation. As I said, you don't need to know complex numbers to handle the various transformation. If you do, it can help. If you don't, it's fine. We'll present different ways to think about the same set of transformation. And you can, if you know to work with matrices, it can help. So I'll talk about it both with and without matrices. That will take us into about 2:35, and then Amir will take over and we'll show you more. And transformation in 3D are waiting for us later in the course. They are not inherently different, but they are different enough that it's good to play with 2D transformations. So just about homework 1, just to remind you, the problems that you don't need to think about in homework 1 is about aliasing. That I start from this shape that fits very, very well into one specific region, into a set of pixels that are very accurate. I'm just playing with overlay, with the video, with OBS to be specific. Yeah. So you have this shape that consists of black pixels on white background. You rotate this shape a bit, and as you rotate it, you see that it partially fits some pixels, and some pixels are fully inside, some pixels are fully outside. Anti-aliasing will mean that we can play with gray level of the shape and set some of them to be more as gray level, depending on how much of the black region and the white region are covered by each pixel. And by doing so, to create some of the artifacts. We'll talk about it in details, but later in the course. Don't worry about it in this step of the course. Show you the gray level of this pixel is determined by how I'll think about this pixel as a square, not as a single point, and I'll measure the area approximately. Usually approximation is just fine, because exact calculation of area is a bit tedious, not complicated, but tedious even in 2D, and the problem will be even more concrete when we'll start to do ray shooting, and then instead of sample just a single point to see if it's inside the shape or outside the shape, we'll sample several points. And those of you who took algorithms with me know that I'm a big, big fan of randomized algorithms that throws coins and make some decision by itself. So the best policy to know what the color or what the gray level of the pixel would be, pick a few random points inside the pixel and check are they inside the shape or outside the shape. And then the gray level is determined by the portion of how many of the sample points are inside and how much are outside. So that's about promo. I think in the last time by now I mentioned typical bugs that student struggles with rotation of the bunny, because you'll see that there are pixels here that just in the target that are not assigned anything. That's why you see white points or black points or points that doesn't mean anything. Again, how do I know what's the value of a pixel in the target? I'll think what is the inverse transformation that take the location of the pixel into the bunny before the rotation. Again, if I want the bunny to be seen as it is being rotated clockwise, I will take the target canvas, rotate it counterclockwise, and now for each pixel, but not missing, for each and every pixel in the target, after the counterclockwise rotation, check where it falls in the original bunny. Don't leave pixels unattended. OK, let's talk a bit about very basic transformations. And at the moment, there is no matrices and no homogeneous coordinates involved. So everything will be very, very obvious. How does the world look like if I'll take every point x in the shape and I'll transform it into the point x plus alpha? And so I'll take the point xy and I'll transform it into the point x plus alpha. And alpha is some constant that I had in mind. And y plus beta. Beta is another constant that I had in mind. What happened to the point 1, 1? It will go into 1 plus alpha and y plus beta. Yeah, what did I say? The point 1, 1 will go into alpha plus 1, beta plus 1. Right? I just shifted this point by alpha to the right and by beta, this other constant that I had in mind, upward. And if you change alpha and beta, positive or negative, your shape will move to the right and to the left. If you are moving beta, it will move horizontally. Change alpha, it will move. I'm out of it today. You'll apologize ahead of time. I'm out of it. Changing alpha, moving it right and left. Changing beta, moving it up and down. Yeah. Somebody should. Yeah. So feel free to correct me when I'm saying something stupid, because it probably was a mistake. Scaling. Here's another very simple transformation. I have two constant s sub x and another constant s sub y. S for scaling. Can you see at the end is a function s sub x, s sub y. And now for every source point x and y, I'll convert the point x and y to the point x times the scaling by x, s sub x, and y will be replaced by s sub y times y. What happened to 0, 0? The lower left corner of the clock. 0, 0 times constants stays constant, usually. So the left corner of the clock stays in the same place. What happened in this example, both sx and s sub y are half, multiplication by half. So the point 6, 6, the upper right corner of the watch, move to 6 times half and 6 times half over here. And this point, which is 6, 0, move to 3, 0. Obvious, right? So nowhere it says that the aspect ratio should be preserved. Maybe you want it, maybe you don't. If you're making sure that s sub x equals sy, the two scaling factors, then the aspect ratio stays the same. But you're just zooming in and zooming out. But if I'll decide that s sub x, the scaling by x, is only half and the scaling by y is actually 2, then the point 6, 6 goes to x will be multiplied by half, so it goes to x equals 3, and y, which was 6, will be multiplied by 2, which is 12. Okay, so that's scaling, but stretching as well. We still call it scaling. And here is a joke that I'm sure that all of you have heard so many times before. So, but we'll talk about this. But this joke is something that I will refer to a few times here. So mathematician has a problem. There is a coffee kettle in one side of the fence. Here is a mathematician who wants to fill coffee and from the coffee kettle. And the question is, what's the algorithm? And the algorithm says, go to the other side of the fence, bring the coffee kettle, go back to the other side of the fence, and pour the coffee. And that summarizes this algorithm. Okay. Now, what happened now if we are solving the next question, which is the mathematician has a coffee kettle next to him, and he wants to pour some coffee. What will be the solution? Bring the coffee kettle to the right side, and from this point it's a problem that we already know how to solve, which is to take the coffee to the left side and pour the coffee. That is, even before I destroy this joke, the point was it's a problem if we have even a non-obvious solution, but we already established this non-obvious solution, then we'll try to recycle the solution for other settings, even if it's not necessarily the most obvious way. Why we solve it in this way? Just because it's a problem that we already solved. We already know what's the solution. Okay. When I'm resizing now I want to resize the clock, but without changing the center. If I'll just scale the size of the clock, I want to make it larger. If I want to resize if I'll multiply the clock by 2, say, then where will its center be? The center right now is at what, 5 and 5? Multiplied by 2, the center of the clock will move to someplace over here. Everybody agrees? If I just multiply the clock by 2 and 2, the center of the clock will move to this place. And I don't want it to happen. I want to make the clock larger, but the center needs to stay at 5 and 5. How do I do it? I express this problem as a sequence of problems that we already know what to solve. Which point don't go anywhere under scaling? Which point don't go anywhere under scaling? 0, 0. So I need to first take this clock before changing its size. Before I change this clock, I'll move it so its center will be at 0, 0. What transformation will it be if the center of the clock is 5, 5? Then I'm taking the whole world and what? Do a translation by minus 5, minus. Now the center of the clock is right here. So far, so good. Next, multiply the clock by 2. Do the scaling by 2. The center stays at the same place because it's in 0, 0. The 3 o'clock note, the mark of the clock that was beforehand at x equal 1 now, will go to x equal 2. You can't see the font here, neither can I. Let's decide that it's 2. The clock is larger. The center did not change. And finally, what should I do? Remember, my goal was to keep the center of the clock right here. And to move the clock from here to here, I translated by minus 5, minus 5. I take x and transformed it to x minus 5. The same goes for y. Now the clock is here. its center is here, but it's twice as large. And now I want to shift it, translate it by 5, 5 to undo the first translation. So maybe we could have got to a simpler solution, but we already know how to solve the problem of translation only and scaling only. So we are just expressing it in this way. It's not hard to compute the formula in this case, but as the set of operations will become longer and longer, we will start to like the homogeneous coordinates and matrix multiplications that are waiting for us. But so far, you don't need any of these matrices or any of the parts. Everybody will hopefully will understand what are the set of transformations that I need to do for each point. Translate, multiply by 2 every point, and translate again in the opposite direction. Shear transformation. So what is a shearing transformation? There are quite a few of them, but one of them can be take x and add to x y, take y and leave it unchanged. So this point, which is 0, 3, let's call it P1, which is 0, 3, x equals 0, y equals 3. Where is this going to? X that was 3 is changed to be 0 still for the x, plus the y, which is 3, because it's how I declared about this point. So we are taking P1 and move it into, help, 3 and 3. But what about P2, which would be 0 and 4? Where is it going? Goes to 4, 4, 0, 0. So it should have been black. 0, 0 stays where it is, doesn't go anywhere. And 3, 0. 3, 0, x, look at the first coordinate, that x is moved to x plus y, so, but y is 0 in this case, and x stays the same. So this point stays the same. Is this a rotational transformation? What in this, if you see these two images, how do you know that it's not rotational transformation? No. It doesn't look like it, but I'll just show you a piece of the picture, of the source and the destination. What really screams here? Yeah. The center move could be happened if I rotate it somehow, depending on where I put the center of the rotation, the axis of the rotation. So is rotational transformation, if I take two parallel lines, if I take two parallel lines and perform it on it, I'll get back to, and perform on these two parallel lines, at some, I take two parallel lines and I perform rotation of L1 and L2. What happens to them after the rotation? Will they be parallel after? The same goes for this pair. Does the shearing transformation keeps parallel line parallel? Yeah. Shearing transformation start with this line and this line. They are parallel to each other. They'll end to be parallel. So if I'll just ask if this transformation keeps parallel line parallel to each other, this transformation definitely obeys, just like rotation. So, but I think that somebody, yeah. You ask about angles. Source angle 90, target angle not 90, not parallel anymore. So it can be actually approximation to a small rotation in small angle because a bit less complicated, but that's parallel lines are transferred under shearing to parallel lines. Angles are not preserved.
Could you shear it the opposite way, so like x and then x plus y?
Thank you. X stays the same. X goes to x, and y goes to x plus y. So now the translation is only upward. But still parallel lines stays parallel. Just the angle change. And of course, you can place a coefficient here, which is 1 in this example, before the y. Place a coefficient and change this coefficient between 0, which will be the identity transformation, to any number that you want, and we'll just stretch it more up and down. And you can combine the two shearing transformation, the two shearing transformation. That is, I can say that in general, x, y will go to x plus alpha y and y plus beta x. Just in the general case, where alpha and beta are equivalent. Rotation. I want to rotate the clock, and we can just play with trigonometry. Immediately, if I want to rotate the clock counterclockwise by an angle theta, then and we'll get to this equation via either convex, complex numbers, or just trigonometry, or we'll describe it as matrix multiplication. Anyhow, either way, you take the point xy, and you want to take this point and make it rotate. There is plenty more animation coming up. I'll take the new location of xy. It will be transferred into x cosine theta minus y sinus theta. What about the new y, the red? The new y would be x sine theta plus y cosine theta. And that's rotation transformation. Let's try to understand it a bit better. Here is my point P. Here is my point P. I'll assume that its coordinates are A and B. And for simplicity, typo, I'll assume that A squared plus B squared over here is 1. A squared plus B squared is 1, implying that the distance of P from 0, 0 is 1. A squared plus B squared is 1. What is B? B is sinus phi for some angle phi. It's not a rotation angle. Phi is just depending on this input point. Every input point has its own angle that it creates with the x-axis. So think about P, you can think about it as its x and y coordinates, which are A and B. Or you can think about it as x, which is the length of this segment, which is 1 in this case, cosine phi, and sinus phi. But this is phi, always. And now I want to rotate it counterclockwise by angle theta. So I want to rotate it by theta. And I just want to convince you that the same will happen independent of this angle theta over here. And it will be the same for every point A and B. How would they get to this point? So P, after this rotation, will go to P prime. P under the rotation will go to P prime. What will be, and here I assume that the axis of rotation is 0, 0. The world is rotating around the 0, 0. In the case of the bunny, you will assume that the axis of rotation is the center of the bunny. But right now, I'll assume that the center is 0, 0. So P prime, where P went to after the rotation, what is its distance from the origin? Da. If P, its distance from the origin, cosine phi square plus sinus phi square is 1, then the length of P prime after the rotation, distance from the origin, should be 1 as well. Right, the animation actually, I think, highlight it. Yeah, I must admit that I was much more efficient with my time before I discovered that GeoGebra can produce GIFs, and that's a huge time sink. But I'm trying to control myself about how much animation you have. So this is theta. That's the angle that I want to do the rotation. Question, if P, its angle with the x-axis before the rotation was phi, what will be the angle that P prime will create with the axis, with the x-axis? It would be phi originally, plus this new angle, the red angle that you see over here, which is theta. Okay, and from now it's just trigonometry. The new, what will be the new x-coordinate of the point? You see the x-coordinate over here, which is the original x, which was A, which was just x prime, assuming that x is the same, x prime is, just by definition, cosine cosine of what? Cosine of the new angle. Everything from here all the way down. All this angle, phi plus theta. Again, phi you don't need to know, you don't need to compute. I'm just using it to convince you, if you care, that the math works for us. Phi you don't need to know. Theta is what you decided to create. You want the image to be rotated by some angle. Okay, so what is cosine of phi plus theta? Why did I get to this cosine? Because the length of this guy is 1, and I ask what is its projection on the x-axis, what's the length of this projection. If this angle is phi plus theta, then the projection has a length cosine phi plus theta. And similarly, the y, the elevation of this P prime, the height value is just sinus of phi plus theta. So the new x prime is cosine of phi plus theta, which is, open your trigonometry book, cosine phi cosine theta minus sinus phi sinus theta. But that's ugly. But hey, what is cosine phi? I know what is this number. It's just the x-coordinate of p before the rotation, a. But this part is just a, the x-coordinate of this point. What is sinus phi? Nothing but b, the y-coordinate of this point. So what did we get? That the new x prime takes the x-coordinate of the input, cosine phi, minus takes the y-coordinate sinus, so the x-coordinate cosinus theta minus the y-coordinate sinus theta. This will create a rotation in the counterclockwise. And just in the same level of excitements that you can barely hold yourself, what will be the new y-coordinate? It's sinus of phi plus theta, which trigonometry, sinus phi cosine theta plus cosine phi sinus theta. But what is sinus phi? It's nothing but the y-coordinate of the input point, b. What is cosine phi? We already know it. It's just the x-coordinate of this point. That's a, very tiny, but that's a. That's b, I don't know if you can see it from above. So you're getting to that the new y-coordinate is a, the previous x-coordinate, the x-coordinate of p, sinus theta plus, notice that here it's minus, here it's plus, the new coordinate, sinus theta. Okay, so you'll have this equation. Why do I like also to use the complex numbers? Because with complex numbers, you just don't need to remember it. You just write it as two complex numbers and remember that multiplication by complex number is just rotation. So there is nothing to remember. And I'll show you another way in a moment how to remember it. Let's talk about another type of transformation, reflection. I want to take this image and reflect it. So reflect it around the x-axis. Not hard, right? What will be the transformation? X stays with the same x. X stays with the same x. And y will be replaced by minus y. Cool with everybody? X stays with the same x, y would be reflected. Now, what happens if I want to start to rotate this house over there, but I want to rotate it around P? Here we are completely in the mathematician and the coffee joke, because we already have all these components. So what are we going to do? We are going to do a sequence of transformation. In the homework one, it's extremely simple to do, and you can do it directly. But I'll also show you tools, if you prefer, where you can do it in a more systematic way. In future homework, you definitely will be asked to do it with matrix multiplication. So what do I do with the house to rotate it around P? If I just rotate the whole world right now, then I'm definitely not rotating the world around P, rotating it around 0, 0. So what do I do first? Translate the house by, or add to xy, what? Minus P. Minus the x of P minus the y of P. So the whole world is shifted, and the corner of the house is moved to 0, 0. So we are in this case. Now you can rotate it together with everything in the whole geometric scene. There is lots of other objects that are also rotated. And now undo the shifting. So add to every point. Convinced? tedious, but you know how to do each step. Let's make it even more tedious. I want to reflect the house around the line y equal ax plus b, and this line is where the base of the house is sitting. And of course, I want to reflect the house and the whole world together with it. But everything around reflection by this line. Help?
Shift the line to be on an axis, and then
I shift the line, sorry. Go ahead.
make it one of the axes, so either the y-axis.
Well, you said shift. So,
So you could track all
no. I start by shifting. I have to start by shifting. That's absolutely right. I shift the whole world, including the line, until it is going through 0, 0. And now, as you suggested, now I can do rotation. And now this line L is coincide with the x-axis. The mathematician in the other side of the fence, if you wish. You know what to do with the house in this case. Reflect by the line and undo everything. Compute B. What is B? Where this line intersects the y-axis. Translate anything by x equals 0 and b equals minus b. The whole world is going downward, including the house that is shifted downward, including the line that is now going through all 0, 0. Now, you can compute alpha. You don't necessarily have to compute it explicitly, but you could do the arctangent, compute this alpha, and rotate by minus alpha. Why minus alpha? Because alpha, rotating by alpha is rotating counterclockwise. I want to rotate the line clockwise. So now the line coincides with the x-axis. So minus alpha counterclockwise. Reflect through the x-axis. Rotate and now undo, and make sure not to get confused about the order. Undo the rotation. Now you rotate counterclockwise by alpha, putting the line back in the right orientation, and undo the shifting, and the order matter. And at this point, you need to ask, does it mean that every pixel needs to go through all this tedious sequence of steps? And the answer is not really, because we'll see that we can create for the whole sequence of operations just one matrix. And how do we get to this one matrix? We'll multiply each individual matrix that describe each one of these operations. We'll create this matrix once. We'll compute their products. We'll see that we just need to multiply a few matrices. And now we just have a single such matrix. What happened with these single matrices? A doesn't care very much what's the complexity or how many operations are involved. It's only a single matrices that now you apply to each one of the billions of vertices and edges and segments that you have in your graphical scene. A, and you doesn't care, and it doesn't matter at all how many operations were involved in creating this single matrix. So A, it's one matrix no matter what. And B, your hardware is optimized to death to do matrix multiplication on vertices really fast and in parallel. Because now at this point, once you have these matrices, you can, if you have two vertices on the house, a few corners, then you can translate this corner and translate this corner and this one all at the same time. which is exactly what GPU would like to do. Okay, so that's where the GPU parallelization is helping you in the game. Optimized to do matrix multiplication, dot product, cross product, multiplying by matrices. Hardware especially designed to do it very fast and to do it in parallel. And at this point, we'll take a break from this, and Amir, would you be so kind? Yeah. So next meeting will end. We'll understand how to work with matrices. It will introduce a bit a slight level of complication because we'll have to, if we want to do translation, we'll have to also know about homogeneous coordinates. Not complicated. Everybody that ever learned graphics also know about homogeneous coordinates, but the studying curve, there will be a shock moment when you'll see it the first time, if it's the first time that you'll see it. But if we want to conveniently work with matrices, which, as I mentioned, homework 1, if you want to, go ahead and do it. We'll give you the code to do matrix products. If you don't want to use matrices, you don't need to, and the complication of homework 1 definitely does not. You can get away without it, without making the homework any harder. Yeah.
Is homework 1 fully released, or is it still?
Still under in the next by the weekend, it will be out. I also want to know that everything is covered that you need to do. Nothing substantial. It's fine, and rotational transformation here, rotational transformation basically, and it's not something that ChatGPT will not give you directly, but give us something if you want to. And there are pieces of bottom that I'm going to show you on the slide there. Profiling the code and everything. That is pieces of code that you can copy from any source, including the database that we give you. Really not about graphics. Just to make the interface more friendly than always open the same file. Or always get the same reaction, just to get it to be more interactive.
Okay. Hello, everyone. Today we go through the template that I will give you through GitHub. On the overlay file, you will have 2 links, one for undergrads and one for grads. We will use GitHub Classroom. You just fork automatically from GitHub repo that I put a template. Yeah, sure. Yeah, looks good. Is that good?
Yeah.
Okay. And okay, basics. So let's go to the. This is not on GitHub right now, but you have one README file. You need to put your name, like if you are 533, 433, and so on. If you use some other files, you don't need it for these homeworks. Just put it here, references, and if you have some special bug that you could not fix in my office hour with professor, but you didn't manage to fix it, you can mention here. Yeah, so that's not complicated. let's go to the HTML. If you forget, even put your net ID is fine, but try to do it. It's just for beauty of the HTML file. You don't need to change anything here on the HTML file. You have just one JavaScript. Let's go through this code and see how it works. So I went through some basics last time. I said how to get an element of HTML from the document. So here you see that we have one input. Input is some like fixed button in HTML for uploading. So the ID is load image inside the HTML file. We have the canvas, the ID is canvas. Single quote, double quote, it doesn't matter in JavaScript. Both of them are fine. I said how to get the context. Now let's go to the functions. So at the end of the code, you see I added a listener for this input button. Let's also open the HTML file. Yeah, oh, that's really small. This is the input button. You see it automatically says browse because it's used to upload the stuff in browser. So I added a listener to this button, and this is the type of the action, the type of event. These are fixed. You need to check like HTML and stuff. When you upload, when you finish uploading, it runs this function. You just put the name of the function. That doesn't need any parentheses or anything else. So here is the function. That's the function that runs when you finish selecting your file. So in this function, there are some extra checks, like if you really selected something or not, how many you selected. So far, you just need one file. You don't need to change anything here. And it just automatically gets the first file. You see input is an object, dot files. That's potentially, I think, I'm not sure. Maybe we can debug right now and see what it is really. We can write down type of files, like what kind of array it is. Also, I need to add something else. I forgot to mention it last time. Remember, we had arrays, objects, numbers, and strings. So the point is that arrays, they need to have the same type. You cannot have like one element being a string, another element being number. That doesn't work. So that's why object might be useful in later homeworks, because you have like different types of objects that you want to pack together. So you have like, let's say you have two scenes, you make an array, two elements, inside each object, different things, and yeah. So here, some log, you chose this file, and then this is the type of the file. For this homework, you need to work with ppm files, which are really simple bitmap files. We'll go through it. That's an object from JavaScript, HTML stuff from browser. And these are all related to the browser. It reads your file as binary string. So the point here is that when we reach to this point, your file, yes, you're right. When we reach to this point, your file is actually being read. So the moment that your file is completely finished, like reading, is this moment. This is, if you know Java, it's like you implement different, like it's like interface and stuff. This is like one default function of file reader. And when your file is completely read by the browser, it goes inside this function. Again, you see function is a little bit, you can define a variable. Like a function can be defined as a variable in JavaScript. But yeah, you don't need these like details. You can just go old school, just programming is fine. So here we get the result. Again, these are some fixed things from JavaScript. There's a function I provided for you that's for parsing the ppm file. So because you read it as binary string, you need to distinguish the pixels, the colors, and so on. So this function is provided for you. It just goes through the header. We will check the image and see how it works. And then remember last time I said each time you select an image, the canvas should resize. This is the place that it resizes. Yeah, so this part is just the lazy part because the ppm file does not have alpha channel. It has 3 channels. Now to just make it like, just have the alpha, I just showed it on a canvas. I just created a canvas, I created the canvas, which has 4 channels, and then I manually copied each pixel. This is from the ppm file, and this is for the image we created from the canvas, which is by default, it has 4 channels.
Everybody, alpha, you all know, but alpha is the transparency.
Yeah.
You have RGB and transparency.
Yeah, so, okay, now let's go to the parts that you need to change. So again, you need to be careful that when you want to write down your animation, because this homework is about making an animation that your image rotates, you need to make sure that your image is completely red. You can do it in 2 ways. First is that you can define like a function to do the rendering. You can start the rendering exactly here when your image completely is parsed, it's completely ready. Or you can start rendering from here, but your image is high likely is being parsed. You can make, I don't know, a Boolean variable is parsed or not. So it renders, it starts rendering, but it checks if the image is it checks the Boolean. So you can make a Boolean at the end of this function. So it just checks the Boolean if it is completely parsed or not. But it's up to you. So the first thing you need to implement, you need to search yourself about the function, is that if you put a while loop here and you say do the rendering, it does not work. The reason is that you will not give like the time for the browser to refresh the page. So you need to use some special functions. There are at least 2 ways to do it. One is from the WebGL APIs. There's a special function. You need to search online and find it. Another one is JavaScript way. There are some functions that you can use to give away the runtime to the browser so that it can refresh the page. Yeah, so again, as a general rule, for purpose of debugging, it's good to write down functions because looking at the variables is easier. Just a few global variables out, and you're good to go. So then you need to implement the functions for rotation. If you are grad student, I mean, it's not finalized, but just in case. You need to also do scaling. And finally, you need to put the image data, the rotated, translated, whatever. So I just put it here for just showing you the image, how it loads. Let's go and select the file. Yeah, so here you see it goes inside the canvas, and the point here is that you need to do animation and stuff. So any questions so far about the template? Yes?
So we can use any file, or do we have to use the bunny?
You can use any file you want, but like when I want to grade it, I remember it needs to have at least like 2-3 frames per second. I will check the bunny. I mean, you can use a huge image and it might be really slow.
Be careful about the format. We assume that it's PPM.
Yeah.
But you can write PPM if you open with anything that opens images, like Acrobat.
Yeah.
Anything you can export it into PPM.
Yeah, also there are some exporters online. You should write down PNG to PPM. There are some stuff. Any other questions? Yes?
Frustratingly, I've been trying to write my own PPM decoder all morning, and so it's good that you did this, so I'll learn something. But so the pixels,
We will go to the image right now. I mean, if that's your question about the format, I can go to the image and we can see the pixels.
yeah, no, I'm just the pixel values are it's a binary file, but they're in hex, so you have to do you have to like do a parse int and like for base 16, or how are you converting the?
Yeah, it's like bytes. So it's like RGB. Each one is between 0 to 255. So it's like 1 byte. So the point.
Byte is stored as hexadecimal.
Yeah, I mean the hex editors. The point is that they don't convert it. They don't try to convert it into character.
Actually, yes and no. The
Yeah.
PPM format was to allow also a higher range of range of intensity. So you can represent each one of the RGB. While in the header of the file, you're saying each value will be 8 bits or 16 bits. They're the only two options. And here we have guarantee. Yeah, here we guarantee 8 bits. So no need to not for it, but to handle the other case.
Yeah, so let's see the image. Let's use a text editor. The text editor tries to convert all the bytes into characters and it fails for sure. But this software is for Windows only. I don't know what is like good thing for Linux or Mac, but you can find it. So if I open it inside the hex editor, so let's have a look. The first characters side by side. This is really small. Can I make it?
While I'm really struggling, I'll warn you about another bug that I mentioned. So I already told you not to try to read from the canvas because of security, and you've got strange bugs when you try to. But why would you even want to read from the canvas? And the reason is, again, talking from previous times that we taught it, was that you want to do an animation of a bunny that is rotated. Like every frame, every 100 milliseconds, it needs to rotate by 1 frame or so. And you might want to attempt to say, I'll rotate the image once by 20 degrees, write it into the canvas, and now when I need to go for the next frame and rotate it by another 20 degrees, I will go to the canvas, read what I have, and just rotate by 20 degrees, so I get the original 40 degrees, which sounds great in theory, but as I said, you cannot read from the canvas. It's not hard to solve it, but every frame needs to start from the input area. That's all part about it. But when you're discovering it, at 2 a.m. when it's about submission, it can get frustrating.
Okay, again, the purpose that we go to the hex editor is that in later homeworks, you may need to save the file. And if you do a bad job, you can go like to the first pixel and track what happens to the first pixel and what you did wrong so that it's like a wrong color. So I'm sorry, it's really small. I didn't.
If you hit Windows and plus.
Windows and plus technology. Windows and plus. Wow. Thank you. I hope I know how to get out of it, but it's fine. Yeah. So. Yeah. Yeah, so as you saw inside the text editor, and these are just characters, 50 is P, like 36 hex is 6, and so on. This is enter. These are like pixels. This 20 hex is a space, and so on. At the end, this is the last enter. Here, the pixels start. So this 4 hex is red color, it's 4. The next one, 0D, it's I can't remember, 13. Yeah, you're right. And this one is 12. So this is 1 pixel. 4, 13, 12. This is next, and so on. Also, you can use GIMP just in case. I found a better solution. If you want, where is it? Well, no, just open. I have nothing else. Just GIMP. Did you open? Yeah. This is cross-platform. At least this one works. If you go to Window, dockable dialogues, and to the pointer, if you select this, now your pointer here on the right, again, if I zoom in, maybe I zoomed in too much, but yeah, you see when I move my cursor, it says what is the RGB value. So you can just see what is the pixel number. And you can just zoom in. This is the first pixel. Again, it goes like this. The pixels that you saw, like goes like one row at a time. Okay, so some obvious hints that you may encounter, but I mean, most languages are passed by reference or passed by like address. That's the same for JavaScript. When you want to copy your image, be careful so that when you just say new image like is equal to this and you change the new image, it will also change the previous one, of course. You just do a deep copy maybe at the beginning of your code, pixel by pixel, and just do a deep copy. Okay, so I think we went through everything. Yeah. Yeah.
How do you get the width and height of the image?
That's inside the top header of the image. You see here, that's the hex. Did I close it? No, it's here. So this P6 is just saying that it's ppm, and this is the width, and this is the height. So technically you have it. That I think it's a global variable. I didn't check, but inside the template, let's see if it is global or not. No, it's not global. You can make it global. Yeah. This is the place that it reads there. Yeah. I will change the template. You may need the width and height. Let me see what else. Okay, there is one thing remaining. When you want to debug, you may encounter, okay, this case I'm showing you I'm not showing you the VS Code, right? But even if you use VS Code or the browser, we can go to the browser right now. Let's go to the browser. Something may happen that can be annoying. This is the web developer. Let's put a random breakpoint somewhere. Okay, so let's put it here. Exactly when the image is done reading. If I refresh and if I select my file, why didn't you stop? Oh, it disappeared.
Oh, because you refresh it. Put the break got rid of the break.
Oh, okay. Oh, I don't know. Well, that's just, it doesn't matter. Let's see how it works. Maybe yeah, it is stopped. So the point here is that if you go inside the variables, did we put it inside? Okay, image data. Where is the? Let's just copy paste it here. Image data. I'm just adding this data. So did I misspell? No. Oh, okay. You see, it took time to show up. I'm sorry, it's really small. I forgot. I forgot. Okay. you see that it took some, I mean, you could not see, but when I wrote down image data to data, it took time to read it. That's because, I mean, browser is not a best tool to debug. Like, if the image is really large and you try to open it, you see browser kind of goes, I'm trying to open this like inside the debugging session. I try, that's like, I don't know, you see it's really large image. It has a lot of numbers. So there is a chance that sometimes your browser runs out of memory if you want to literally stop at the debugger and open the image. It's like 1,000 by 1,000 and see what is the red channel of like the 100th pixel. That's kind of tricky here. I mean, that's one downside of JavaScript and browser is that when you want to debug, if the image is really large, you may run into like some issues that the tab crashes and stuff like that. You need to refresh. So that's the point that console.log helps you more, because you may try to open some really large image and it may be kind of slow. Sometimes it's good, maybe close other tabs inside your browser to save some memory. The point is that for security reasons, if you have a 64 gigabytes memory, you cannot use it by your browser for security reasons. And even each tab has some memory limits of inside your browser. So just be careful. If you want to load a fancy image, it's fine, but if you want to debug it and really open it inside this debugger, you may crash the tab. Let me see, any other hints?
Remind them of what I cover it next time, just how you made the image into one array, and how do you decide about the address of each one?
Yeah, sure. So we can even go and see how this image works. If it says, oh yeah, it says that's uint clamped array type. So in later homeworks, you may need to define some float images. So again, these are objects. Let's write down a little bit code instead of using templates. To define such typed variables, by typed I mean it has bitness, we can define something like my array is equal to new float, I can't remember, but yeah, something like this. And yeah, so here you need to write down what is the size. So if I say width, like multiply by height, multiplied by 4, that's 4-channel image. So that image, red image.data that you saw inside the browser, it's nothing but some sort of object like this. So in future, when you go to some images that they have, they're called like HDR images, float images, you may need to manually define it. And remember, it's just one gigantic array. Yeah, I think I'm done. Anything else, Alan? You? Yeah.
First time in my life.
Also, there is another point. Inside the ppm file, there is a max value. So ppm file can handle more than 1 byte in theory, but this parser does not handle it. Just be careful. When you convert your image, just be sure that it's 24-bit image, not more. Because some converters, they may go like 2 bytes for each pixel. I don't know, not 2 bytes, like 2 bytes for each channel. Yep.
To mention that the big question about VI versus Emacs was replaced by, are you working in the Explorer directly, or are you working in Visual Studio with the right plugin, and which plugin is the best for you? think that it's a bit personal taste. You have all the options. Visual Studio with white plugin will be fine, or just work directly with the browser.
Yep.
Thank you. Thanks a bit.
Oh, okay, you're welcome.